let me introduce Dr. Aybek Korugan from Boğaziçi University, Industrial Engineering. So he's a old friend of mine. We've been doing some work together and stuff. And actually, some of the work we've been doing together relates to closed loop supply chains. So which has to do what he's going to present today. But yeah, today I believe what he's going to present has to do also how bullet effects is manifested in such systems. So actually, I knew he was doing some work on this with his master's student and stuff. So it will be very interesting to listen to him today and see and understand what they have done. So it's very nice to have you with us, Aybek Hocam. And
Thanks very
so
much for this.
the floor is yours, please.
Thanks very much for this great invitation. Let me start by sharing the slides. I guess, does everybody see the slide? Let me also...
Yes, no problem.
Okay, great. I hope it's not the slideshow. Okay, so so my objective today is to present one of the joint work with Gönenç Yücel, who's one of our professors here, and Nurgün Doğdu. Nurgün Doğdu was our master's thesis student, and she worked on a model that would analyze the bullwhip effect in closed-loop supply chains, in a sense. She was the second of the students who actually worked on this problem. The first student worked on this problem in an uncapacitated production context. Nur added capacitated production and some other bells and whistles into the structure. And as Murat Hoca said, this actually basically relies on the idea of how closed-loop supply chains basically operate. So let me just give you first initially a picture of how we reduced the whole problem into a subset of rectangles and triangles, and the circles are the most important here, I guess, is this. So basically, when you look at a reverse or a closed-loop supply chain, the essential idea is that there is a manufacturing body that produces something based on demand, and that demand actually, that demand actually is satisfied through the efforts of distributors, wholesalers, and retailers. So it's conveyed to the customer eventually. The customer seizes the product, uses the product, and then with some certain probability returns the product to the original equipment manufacturer. Doesn't have to be always the original equipment manufacturer, obviously, but it is actually one compact problem that has been studied in the literature closely, because there are quite a number of reasons why OEMs want to do their remanufacturing by themselves. And sometimes they have actually contracted out remanufacturers with themselves, and sometimes it's just, free remanufacturers. But this one problem actually arises quite frequently. There are quite a number of manufacturers that do that. For example, Hillrom, that manufactures hospital beds, does remanufacturing quite frequently, and they are actually sort of using this structure in the context of servicizing, where they do not sell the product, but the service of the product, not the product itself. So there are quite a number of companies like that. So this structure is not unfamiliar in that sense. So the one thing that's interesting is that in the past, the return was a black box, basically. And the joint idea of Murat Fadıloğlu and I actually comes in here into play. When you look at the return as an average rate, okay, in a saturated mechanism, then you actually estimate one rate and prepare for that. But in reality, this is actually this can be considered as an infinite server queuing system where each server is actually a customer that uses the product. At the end of the product, they actually send the product back with a certain probability. So then you actually kind of need to keep track of how many people are using what product, basically. And of course, if the product lifetime is non-exponential in the sense of modeling or in the sense of behavior, then you're going to also keep track of when you actually sold the product and how long it's going to be used. And so the prediction of return becomes important, because when you look at the original manufacturing system, the only uncertainty comes from the customer. Everything else is actually settled, like in most cases, like raw material and so on and so forth. But when you generate a closed loop supply chain mechanism, then this return has a randomness, and that randomness includes how many products are returned at which time, under which condition. All of these have to be actually sort of predicted, okay? So that prediction can be done better by looking at the number of customers that are using it closely. So that's the essential idea of this study in that sense. Obviously, since we are considering a bullwhip effect, that means multiple decision makers are going to predict demand in one way or another and just ask for products from an upper echelon. So basically, the retailer is actually the initial estimator here. So generates an estimation, pads it along with, with his or her safety parameter, whatever that is, maybe a fill rate practically, and conveys it to the wholesaler. Wholesaler actually sees demand by itself from the retailer and pads again for its sake, and then sends it to distributor. Distributor sends the information to the original equipment manufacturer. Basically, that actually sort of generates. That's one of the reasons why we have a bullwhip effect, basically. Okay, so that's the idea. So in this original mechanism, this is how it works. And the question here is, what if I introduce the returns? Because if I have returns by themselves as a rate or as a distribution, I wouldn't be actually considering the link of customers buying the product from the production body and bringing it back to that production body, basically. Okay, so that link is not there, basically. Okay, but when you produce that link, one wonders whether this information is going to increase or decrease the bullwhip effect, the variance in the system. Because originally, if you don't consider this link, you're adding just one more random variable to the sum. Obviously, this is going to increase the variance. Okay, that's expected.
Aybek, sorry, can I ask something?
Sure.
So does the manufacturer, is he capable of observing when the product goes into orbit from the retailer?
No, this
No.
information is not conveyed to the manufacturer.
Okay.
The
So
manufacturer has to predict, basically.
okay. So that's not. And do we have inventories at different levels of the echelon?
Yes, each mechanism has an inventory. So there are triangles that we've omitted because
Okay.
the picture
Okay.
would
Thank
be
you.
large. So no problem. Okay, so that's the essential idea. That's what we're basically observing. Obviously, I just wanted to add the idea of bullwhip effect with one simulation output that we had generated for presentation purposes from the past. basically. This is the bullwhip effect of an original equipment manufacturer without a return flow. That's what an OEM sees actually all the way until the producer with the number of orders that are produced, basically. So our objectives then in that sense is, first of all, we can see that reverse logistics has an extra potential of kind of addressing the supply chain risks and or environmental concerns by reusing whatever exists. Quality, timing, and quantity are going to be the problem, though, when you actually get products from users, okay? And therefore, a more accurate estimation of what's coming, when is it coming, and in which condition is an issue. Of course, the quality is not included in this specific study. Quantity and timing actually are of interest for us. Before we delve into it, we've just gone through a little literature review. Actually, there is not much done for reverse logistics and bullwhip effect contexts. There are some studies, but none of them are considering an orbit or installed base, basically, the products that are in use, essentially. So Denso Diaz looked at the process and found that the average product lifetime and remanufacturing capacity do not have an impact on the bullwhip effect. But here they are looking at a deterministic system by using system dynamics approach. So the delay of product lifetime is actually deterministic. Ponte and company actually observed the smoothing effect of the production capacity constraint on order variability. So that's one issue. Obviously, when you introduce production capacity into the system, into the model, actually you're going to see that the bullwhip effect is going to be smoothed out, obviously, because there's a capacity, then there's an upper bound. Obviously, in that case, the bullwhip is going to be smoothed out, but the stock variability is going to increase because then you are going to have uncertainties in that sense. Obviously, in this study, it's just a classical supply chain, so there's no return flows. Obviously, one of the most important things in controlling the bullwhip effect is sharing the information, collecting and sharing the information, as much information as possible. And Jeong and Hong actually have shown that if you share not just demand forecast information, but the total order history with the whole network, then the bullwhip actually reduces. Again, this is a no remanufacturing system. Pardon. Okay, there. This is very counterintuitive. So Lin et al., on the other hand, looked at a closed-loop supply chain with 4 echelons just like ours. And they show that the demand estimation increased the bullwhip effect. And this is actually something that we have observed as well. But they did not look at the return estimation methodology in the production capacity. Huang and Diu show that the bullwhip effect is greater in a closed-loop supply chain than the forward supply chain, regardless of the return rate. They assumed capacitated manufacturing and remanufacturing, but disregarded the impact of return estimation. So they didn't make any return estimation. They just actually considered whatever comes in and planned over that. Quing et al. Found actually conflicting results where the closed-loop supply chain had lower bullwhip, but they modeled incapacitated production. So there's actually some issues here, basically. So that's why we wanted to look into this problem a little closer in that sense. Okay, there. So to this end, we've modeled this structure where customer generates a demand one by one, one per day in this case for the numerical reasons, for the numerical study. And we've fixed that to see the differences on other processes. And we assume that the demand process is a Poisson process, so large enough uncertainty, basically. We've always considered a production capacity that is slightly higher than the customer demand. And initially, each system uses an RS periodic inventory replenishment policy. So R is the period length, S is the up to S order level, and the difference between the inventory and S that is calculated for that period is ordered upstream. Basically, that's how it actually goes upstream. And all the demand forecasts are done using moving average methods, and we've changed the methods of moving average, parameters of the moving average in general. We've assumed production capacity, and the production capacity is assumed to be slightly higher than the demand that comes in, basically. And when I say demand that comes in here, we assume that retailer has a lost sales policy. So whenever there's no demand, they just don't sell whatever the product is, and the demand is lost. But the retailer still observes those demand points and makes the estimations based on those values. So that actually information comes into the system. And wholesaler and distributor have back orders. They do not have lost sales, basically. And so does the manufacturer, so does the serviceable inventory in general. Therefore, actually, the actual demand is seen through the system. And the capacity of manufacturing is slightly higher than that actual demand. So, for example, if you're looking at a 7 days review period, then we set the manufacturing capacity to 8 because the average demand the retailer sees is 7, for example. So that's the balance, basically. So the utilization of the manufacturing side is not low, let's say, but it is not unstable. We assume that when a returned item it comes into the system, it's remanufactured. And when they are remanufactured, they can actually satisfy an existing demand. There is a return probability P. So when a product is actually out of use, it is discarded with probability 1 minus P without coming into the system. Initially, we assume that this product lifetime distribution is exponential initially. Okay, so this I have actually stated, stock out leads to lost sales only at the retailer. That's the structure. So in order to be able to analyze this, we've used discrete event simulation. And the structure of the discrete event simulation is such that all of these items, so all of the products in orbit, basically, are individual entities, basically. So they are all objects, practically. And we have to actually keep track of those. So when we look at the return estimation, which was not considered by other studies, we've used 3 different methods. One of them is moving averages. So that in moving average, we don't have any information. We just look at the returns at the end of each period and estimate the average value and its variance, basically. The second one is the orbit size information. So in that case, we assume that, of course, this is an assumption, it's not predicted. We assume that somehow we know how many products are in use. This is basically an assumption, obviously. It's not, it may not be realistic, but it gives us a bound, basically, in that case. And to understand how important this orbit size information can be. And we estimate the average returns based on this information, practically. Obviously, the rest is estimation because P is, it just occurs however it occurs. R is, again, the same review period that we have. And gamma is actually the rate of a product coming back, right? Basically. And since this is a Poisson process in that sense, its variance is going to be the same as its mean. So we are going to actually have that. And the third method is advanced return information. That's the best possible scenario that can happen. You know exactly what's going to come back. That's basically it. Partially, this is true. This may be true. In some cases, it is not unrealistic. It's less unrealistic than knowing the number in orbit size. Of course, when you have advanced return information, then you can actually do that. But for example, in service sizing cases, you have contracts. And based on those contracts, you know which products are going to come back to you. Okay, so now how the information is conveyed in the upstream towards the upstream information of orders and how the orders are fulfilled towards downstream are quite important things in terms of bullwhip effect itself. So we have 3 policies. One of them is the base policy. And in the base policy, the downstream echelon orders the amount between the S it calculated and the inventory level. Inventory position, not inventory level, inventory position, okay? And it also adds the change in the safety stock, okay? So it has that. And the order goes to the upper echelon. The upper echelon ships the order when everything is ready. So wait until everything is ready, basically. In the simplification of that system, we deduce the safety stock policy. So there is no safety stock buffer in here because actually when we are calculating up to S, the S value, we are including some buffer in itself already. So there's no point in that. So we cut that and see to see the effect. And the third is the batch shipment policy. So lower echelon sends upper echelon a certain amount. Upper echelon sends whatever there is in hand as soon as it can, basically. It doesn't have to be the whole order. So the order is actually partially fulfilled through time. So to analyze this, we have generated, as I stated, a discrete event simulation model. It actually looks at periodically because everything changes in periodic manners. To this end, we looked at a system that has a warm-up period of 2,000 days. So 2,000 days are roughly 2,000 demand points. And after deleting that data, we've looked at 30 more batches of 2,000 days. So we're looking at actually 62,000 days of simulation. Obviously, when you have R15, for example, one of the values that we have, and moving average has a value of 30, then you need 450 days of data. So that is actually also dissolved in the warm-up period. So once the warm-up period is gone, you actually have a working system altogether. Initial experiments were done based on the return probability, reorder period, number of moving average periods, and average product lifetimes. Average product lifetimes initially are exponentially distributed. So we looked at the return probability between 0.1 and 0.9. We've looked at two reorder periods, 7 and 15. We've actually also looked at the reorder period of 1, but reorder period of 1 is actually continuous review policy, nothing else. So there's not much of a reason to report that. The number of moving average periods for demand estimations were 15 and 30, and also the return estimation. And average product lifetimes were 360 days and 1 year and 3 year products. So on the average, a product is used 1 year or 3 years. So 1 year is like fast-moving products in a sense, like a telephone or something like that. 3 years are more like something that resembles hopefully not dishwasher or things like that, essentially. Okay. Our performance metrics are as follows. The most important one is the bullwhip effect itself. We measure the bullwhip effect as the ratio of the order variance at echelon K to the demand variance. The net stock amplification is the ratio of the net stock variance in an echelon to the demand variance. Order cycle time, which is quite important because in the first two methods, actually, the third one as well, until the total order is fulfilled, it's going to take some time. You place an order. Until the order comes back, it may take more than one period, more than one order cycles. That's a possibility. So an average order cycle estimation is important. So order cycle time is also measured. The higher the order cycle time, the higher the order amounts towards the upstream, and higher the uncertainty, obviously. And average fill rate is actually the probability of a demand being fulfilled at its first occurrence. So when the demand of a customer comes in and is fulfilled, then it's within the average fill rate, basically. Okay. Now, initially, we've conducted 20 experiments based on the parameters. So these parameters using the Taguchi orthogonal array method with the Taguchi with 20 experiments. And what we are reporting here is the average of those 20 experiments. So it doesn't have the return probability, or everything is included, basically. And this practically is the forward supply chain's behavior in terms of bullwhip effect. Obviously, in the forward supply chain, the return products the return probability doesn't have any impact in that sense. So as you see, the retailer and OEM have the lowest bullwhip effect. Wholesaler and the distributor have the highest bullwhip effect, obviously, because they actually see the highest uncertainty. And the reason OEM doesn't see the uncertainty this much is because it actually has a finite capacity. So there's a certain amount of things OEM can do practically. When we compare the bullwhip effect to the return flows, so when the return flow comes in, let me remind you that there are three methods of estimation of returns, moving average, knowing the average orbit size, and advanced return information. Okay. In terms of retailer, as the return probability increases, initially the bullwhip effect actually is lower. Then it actually increases, so it becomes higher than the bullwhip effect that I reported for forward supply chain, but then it actually gradually decreases as the return quantity increases all the way almost to up to minus 40% in terms of retail. The wholesaler also has a similar picture, practically. So does the distributor. Actually, distributor sees the better end, the best end of that. But when you look at the OEM actually has uncertainty from both ends now, both from the returns and the demand on both sides. And as you see, it starts out to be actually higher than the forward supply chains case. And then slowly it reduces, okay, when the returns actually exceed 70%. The return probability exceeds 70%, basically. And there is not much of a significant difference between the estimations as we see for them. This is the inventory effect, basically. The uncertainty in the inventory for the original equipment, for the forward supply chain. And similarly, so this actually goes for all four performance measures that we have. As you see, actually, knowing more with the advanced return information for the retailer is a better idea. It actually brings us more information in that sense. And the inventory variance actually reduces in the retailer. Starts out from 40% and lower. When we have moving average and orbit size estimation initially is not performing that well in this case in terms of retailer. Initially, when there is low probability, how does that? Low probability of returns. But as the probability of return increases, that means actually our estimations are actually get better when using the orbit size information, basically. So in all three three of them, orbit size estimation actually gets better as the return probability increases. In most, actually, no, all of these, basically. But see, while the inventory uncertainty is reduced for retailer, wholesaler, and distributor, uncertainty of inventory actually is increased significantly for the OEM because of returns. Because whatever return comes in, we just let it in practically. And that's the essential issue. So we are actually holding more inventory than expected. And when we consider the returns, remember I had said earlier that the capacity of production is almost is very close to demand. So the utilization is quite high in the system, okay, for the forward supply chain. When the returns come into play, actually they release some of that tension of the high utilization. They take out some of the burden, but the inventory of OEM actually increases. So the third performance measure in that sense, average fill rate, okay? And when you look at the average fill rates of the forward supply chain, retailer has about 90, that's a good thing. And wholesaler and distributor have lower rates, and fill rate of the OEM is much lower. And retailers' fill rate does not change much with the return flows. And so does wholesalers. It actually sort of reduces a little bit. And distributors doesn't change much. But again, OEM's fill rate actually is more than doubled as the return rate increases. So this is actually in par with what we've seen with the previous results. And the order cycle time is the fourth performance measure that we were interested in. So the order cycle time between wholesaler and retailer is, for example, in the original forward supply chain is 18, and then goes between distributor and wholesaler, it's 12, and then OEM and distribution is 15. Of course, these are averages, so I didn't report the half widths with that. I'm aware of that. I'd like to remind you that as well. But as you see, these values change as the returns come into play. And with 0.5, it's the lowest decrease, let's say, but the rest is quite nicer for the wholesaler retailer ratio. So the response to demand actually is faster because of the returns, because there is more returns in the system. And similarly, with the distributor wholesaler relations, as the returns increase, come into play, the response actually increases, okay? And OEM to distributor obviously is getting much better as the returns increase practically, because the capacity of the OEM actually gets higher. When we compare the bullwhip effects in terms of reorder periods, because all of the reports that I've given so far were actually based on the average of the 20 experiments in that sense. As you see, this is the forward supply chain. FSC here is the forward supply chain. For retailers, it's comparable the bullwhip effect, with and without returns. For the wholesaler, you can see that returns actually have an impact in terms of bullwhip effect. But moving average orbit size information versus advanced information, they do not have major differences, basically. In the distributor, the same thing is actually visible. As you remember, initially the bullwhip was highest in wholesaler and distributor. So the returns are actually benefiting them the most. And OEM, on the other hand, does see some improvement, but it's not as high, basically. But in all cases, the returns are actually going to have, in all cases, actually, the bullwhip effect is slightly higher for reorder period of 15, which is expected because the time increases, uncertainty increases, basically. And yeah, this also gives the differences in terms of in a graphical structure for 3 different cases. We've actually looked at whether there is a statistical significant difference among these estimation methods. In terms of wholesaler, it's obvious. In this case, there is some statistical significant difference. But in general, there's not much of a difference between moving average or OS and ARI, advanced return information. And this is actually the ANOVA for that. So this portion is a bit more statistically significant, basically. So for supply chain, moving average and orbit size knowledge. Okay, so the difference here is statistically significant for both from retailer to OEM. And for this, only OEM side has actually statistical significance. And in general, actually, there is some, so one can say there is a statistical significant difference between the estimation methodologies in that sense. Now, one other effect is how you collect the estimation information, which is actually the moving average periods. So we have 15 and 30. Obviously, if you have higher data, then you are going to make better estimates, let's say, in terms of averages at least. So in here, therefore, the bullwhip effect, when looking at 30 periods averages in terms of estimation, is better than 15 periods. And this is actually for the forward supply chain. And the differences here are when we have the returns as well. So return estimates are given here. And as you see, for the retailer and the wholesaler, making the estimates for 30 periods is reducing the bullwhip effect more, while for the distributor and OEM, although in both cases the bullwhip effect is much less than the forward supply chain, the impact of using 30 instead of 15 periods is less, basically. So this is an interesting thing to report as well. And when you look at these cases in terms of average product lifetimes, which is quite important in terms of estimation of returns for both orbit size information and moving averages. As for the retailer, as the average product lifetime increases, the bullwhip effect increases, basically, from negative to positive, basically, when compared to the forward supply chain. For the wholesaler, moving average and advanced return information do not have major differences, but the orbit size based estimations actually have an impact. So in that sense, so their estimations are not actually helping the bullwhip effect. Wholesaler and distributor have a similar depiction. Actually, OEM also has a similar depiction. And OEM actually, in this case, in both cases, has presents higher bullwhip effect than the classical, than the forward supply chain itself. So again, the bullwhip effect of wholesaler and distributor are actually reduced. And one other thing that of interest for us was the product lifetime variability. Now, remember, we had done the experiments with exponential product lifetimes. And initially, we have conducted a product lifetime distribution with 720 days. So it's the average of these two. To see the distribution impacts in here. So here we've used log normal initially, and then with the same averages. And review period is 15. Moving average estimation period is 30 for all of them, and average return probability is 0.5. And we've calculated for different coefficient of variations of these distributions, how the impact actually can be seen. And as you see, if we use usage distributions as with heavier tails than exponential, let's say, particularly in Weibull, in both cases. And then the bullwhip effect actually increases. Okay, so it's positive, as you see, with coefficient of variation increasing, the bullwhip effect increases, basically. In Weibull, that increase actually is quite more significant because of the heavier tail of the distribution. So that actually is a major difference from the exponential model. Okay. And alternative shipment policies was one of the things that we had discussed initially as parameters. So base policy, no safety stock policy versus bad shipment policy. We have compared this, these not relatively, but absolutely. So we're not comparing them with the forward supply chain directly, but we have the forward supply chain here, moving average values here. and the orbit size estimation, advanced return estimation information cases here. As you see for batch shipment, the bullwhip effect almost doesn't change in almost all cases. In distributor, advanced return information slightly increases the bullwhip effect, basically. But in the OEM case, from forward supply chain and on, actually the bullwhip effect increases slightly, okay, in all mechanisms. But base policy and no safety stock are quite impactful, both for wholesaler and the distributor, and return information or return information estimation, actually, as it gets better, reduces the bullwhip effect quite significantly in this case. And finally, I guess I can skip these two, the impulse demand case. This is actually the pet peeve of our student who actually wanted to study what happens suddenly the demand increases and decreases. How does the system respond to that? Was the essential idea. She is more inclined towards system dynamics approaches. That's why she wanted to see that. But since the system, again, converges to the average behavior, the results are similar to what we can see actually from the previous results. So, okay, let me get to the conclusion finally. As far as we've observed in these experiments, that production capacity smooths the order and inventory variability at the OEM, obviously. We've seen that the return flow had varying impact on the echelons. It increases the production variability, but reduced the bullwhip effect in downstream echelons. And only the highest return probability reduced the bullwhip effect for all echelons. But for the echelons in between, actually return probabilities are quite useful. That's what we've seen. Reorder period length had a significant impact for the forward supply chain, but not for the closed loop supply chain. Higher number of moving average periods resulted in lower bullwhip effect. Average product lifetime did not have a significant impact on the bullwhip effect, basically. The average didn't, but the distribution did, actually. We've seen that. Alternative shipment policies with no safety stock and batch shipment reduced the bullwhip effect. But then again, the costs must be considered here. So if you just keep shipping whatever you have in your hand, you're actually incurring some repetitive costs of shipment, fixed cost of shipment. Return estimation with orbit information did not have a significant impact on the average bullwhip effect under steady state conditions. Return estimation with orbit information had a significant impact for the short-term horizon and impulse demand. And product lifetime distribution has an impact on the accuracy of the orbit information. So those were the things that we had actually we observed. in general. And I guess at this point I can stop my presentation and wait for your questions and your comments. Thanks for listening.
Thank you, Aybek Hocam, for this very interesting presentation. So at this point, I'll turn the floor to audience for their questions. Any questions?
Well, I have a small one. Yeah, based in your assumptions, you don't assume that the customer returning the product do not request a replacement, right?
No. This. I mean, we did consider that in the thesis. So this is actually one of the future studies. I didn't put the future studies in there, but this is going to reduce the variability quite significantly.
Oh, okay. Yeah. All right. Thank you.
Okay.
So, any other question? Okay, then Aybek Hocam, thanks a lot for sharing your time with us.
Thanks very much for inviting me. It was, even virtually, it was nice to see you.
The same goes here, although I see you more frequently. It's always a pleasure. Thank you.
Likewise. Thanks very much.